So in chapter 5, we're going to talk about grams, moles, Avogadro's number. We'll also talk about percent composition and empirical and molecular formulas as well. So we'll get into it here. I have a calculator. That's good. All right. Okay. So chapter 5. The first thing we're talking about is atomic masses, and a reminder that the atomic mass can be found on the periodic table. It is actually that number that is on the bottom there. So as we talked about when we talked about atomic numbers and mass numbers, that number that we see on the periodic table, again, is not the mass number, and it is that number that is there on the bottom. That is the atomic mass for a particular element. And obviously, one of the fundamental properties of atoms is obviously its mass. But obviously, it creates a problem as they are very, very small things. And obviously, you can't just like pick up an atom and pop it on a scale or anything like that to measure it. So very oftentimes when we cannot sort of measure directly something, definitely in science and especially in chemistry, they oftentimes will choose something to use as a standard to sort of compare everybody else to. And sometimes they'll assign the standard a certain value. And in the case here for atomic masses, which is obviously their mass is related to the number of protons, electrons, and neutrons there are, they did choose an isotope of carbon. Remember that isotopes, again, are really the same element, but they have different masses because they have different numbers of neutrons. And they chose the carbon-12 isotope to use as sort of the standard to sort of calculate the atomic masses of every element that is present there. The carbon-12 isotope has basically 6 protons and 6 neutrons and has a mass of 12 AMU, which is atomic mass units. So this carbon-12 isotope has a mass of 12 AMU. Now, AMU is a unit of obviously atomic mass, as it's said there, atomic mass unit. It's a unit that we don't really use too often in normal sort of chemistry calculations, but it is technically sort of the number that you could get from the periodic table. So, for example, if we did look at hydrogen, and it's 1.008. Basically, you could take that number and say there are 1.008 AMU in an atom, basically, of hydrogen. So you could kind of use that as a conversion factor. We will obviously in this chapter, not too long from now, we'll talk about really a more usable unit that we use in terms of those numbers on the bottom, which is molar mass, which is the grams per mole. So AMU per atom is another sort of unit that you could kind of use for those numbers that are on the periodic table. But I would say, again, probably 99 times out of 100, we'll use it as sort of molar mass, which we'll talk about as well here coming up in some different sort of units. An AMU is basically 1/12 the mass of a carbon-12 isotope. So atomic mass, which is atomic weight, is also used to be referred to, can be found on the periodic table. So as I said, they sort of used carbon-12 as the standard. They did some experiments and it showed that, you know, for example, hydrogen is only about 8.4% as big or massive as the carbon-12 isotope. So really, you know, that's one way they could kind of get the number that we see on the periodic table. That's basically 8.4% converted into a decimal, right? Move it 2 places to the left or divided by 100. We'll do that for you. And we get something like 1.008 there for hydrogen. Similar calculations, again, for all elements can be found on the table there. So oxygen there is basically 16. And again, that is our number on the bottom. And we can use that as 16 AMU per atom, basically, as a sort of conversion factor for it. Again, 5585. In terms of atomic mass, or really in terms later when we talk about molar mass, when we go to the periodic table and we sort of use those numbers, it is very common and probably proper procedure that most people will take it to 4 significant figures, those numbers that you find on the periodic table. Depending on your periodic table, there may be a lot more than that. There may be a lot less than that, depending on the periodic table. But typically speaking, you usually will take it to about 4 significant figures whenever you're sort of using that number that you find on the bottom as either the atomic mass or the molar mass when you're doing calculations. So this does bring up something that we do see, for example, when we do look at carbon on the periodic table. Carbon is actually listed as 12.01 on the periodic table. And you may say to yourself, when you're having this conversation with yourself, what's the deal there? It is carbon 12, which is our isotope that we're using for the standard, has a mass of 12. Why does it say, for example, 12.01 when you look at, say, carbon on the periodic table? And that's really for a very specific reason. And the specific reason is what we do see on the periodic table is really the average atomic masses. Although most people don't call them average atomic masses, they just call it atomic mass or molar mass, but they are averages. And what they're averages of are all the naturally occurring isotopes for a particular element. So all the naturally occurring isotopes, say for carbon, and we'll take a look at the calculation in just a second, basically comes out to 12.01 rather than 12. So what we're really looking at when we use those numbers, or really any periodic table, is really an average value of those naturally occurring isotope. There is a sort of calculation that you could do to calculate that. And if you wanted to calculate the average atomic mass, you basically would do a couple of things here. If you want to calculate the atomic mass, you would take the percent abundance or relative percent abundance. That's basically the percentage at which that isotope occurs naturally. So obviously 100% would be all of them, right? So you could have an isotope that occurs maybe 40% of the time. You could have another isotope for that same element that maybe occurs 60% of the time. So you take the percentage of that first isotope, and obviously you would convert it into a decimal when you're doing the calculation. So you could either divide the percentage by 100, or like I said, move the decimal point a couple places to the left to do so. You would times it by the atomic mass of the first isotope. And then what you do is, where a lot of people mess up because they want to multiply at this point, but you're actually going to add, and you're going to add it to the percentage of the second isotope times the atomic mass of the second isotope. And then obviously, depending on how many isotopes you may have, you just really continue that pattern of kind of the percentage of the isotope times the atomic mass of the isotope and add them together. And this will really give you pretty much the values that you sort of see on the periodic table for those average atomic masses. Obviously a little bit off with some rounding, but that's typically how those numbers come from. Now, as I mentioned before, when you are perhaps given a problem like this, you should make sure that all the percentages add up to 100%. Otherwise, you are missing an isotope somewhere, right? And if you happen to have some isotopes and they do not add up to 100%, then you could really figure out, the missing percentage by subtracting from 100 after adding up all the percentages. So there are some ways you can kind of figure out those type of things. But again, if there's sort of 2 naturally occurring isotopes, you do that, 3, however many there may be. That is basically how we would do these sort of calculations. So if we look at something like carbon, for example, carbon has 2 naturally occurring isotopes. And it's carbon 12 isotope and carbon 13 isotope. And we see that basically the carbon 12 isotope occurs about 99% of the time, and about the carbon 13 isotope occurs about 1% of the time. And the carbon 12 isotope, as we talked about, has a mass of 12. The carbon 13 isotope, as you can see, has a mass of 13.00. So that is the calculation we were just talking about. So I'll rewrite it here just to make sure. So we would calculate the atomic mass by taking our first percentage, which is 98.89%, And again, you can just move the decimal point a couple places to the left to convert it into a decimal. We would times it by the atomic mass of our first isotope, which is our carbon-12. That's basically our carbon-12 isotope there. We would add it to the percentage of our second guy. Once again, you can move the decimal, or if you wanted to, you could divide by 100, which would obviously move the decimal place for you to do that, times our mass of our carbon-13 isotope, 13.00335. And that's our carbon-13 isotope. And again, when we add that together, we got 12.01, which is, again, pretty much what we see on the periodic table. So this is what we're referring to as them being basically the average atomic masses of all those naturally occurring isotopes. Obviously, we just quickly look at the percentages. We're about to 100. When you do add up the percentages, it may not be perfectly to 100, but it should be in kind of that 100 ballpark, maybe a little bit above it, maybe a little bit below it, but it should be pretty close to 100 when you do that. Any questions on it there? It is also important to know that really you would never find a carbon-12 atom if you could pluck one out that has a mass of 12.01. You would either be plucking out a carbon-12 isotope or a carbon-13 isotope, which obviously has their respective masses. So you really wouldn't necessarily find one that, does have a mass of 12.01. Any questions on that there? So as I mentioned before, atoms are very tiny. So this atomic mass unit, just for reference point there, is about equal to 1.66 times 10 to the minus 24 grams. And as I mentioned before, not too much of the time that we use the AMU sort of unit. We use that sort of grams per molar mass because it's a more representative unit of what we do with it a lot of times. All right, so that's it. So again, you could use it as a conversion factor, and again, you would take it to 4 significant figures, and that's basically what you would get as we were talking about. We would take that from the periodic table, and again, sort of like grams per mole, this would be AMU per atom is basically how you can use that. So if we wanted to know the mass in AMU of 431 atoms, we would set up our dimensional analysis here using this early as a conversion factor, which, by the way, obviously, if you needed to, you could flip it the other way if you were doing some opposite sort of calculation. In this case here, as we can see, our atoms will cancel and leaves us with about 5176 AMU as the mass of those 431 atoms in this particular case. And if we did it for something like aluminum, if we went to aluminum off the periodic table, once again, you would see 2698 on the bottom there. And that again would mean 2698 AMU per atom. Or an atom is 26.98 AMU. So those are really sort of 2 conversion factors that you could use. And in this case, we're looking for the mass in AMU of 75 atoms of aluminum. So once again here, we could set it up as a conversion factor. And atoms on top, atoms on the bottom will cancel, giving us about 2024 AMU as the mass of those atoms. Now, you may be wondering, maybe how do you know maybe the percent relative abundance of each of these sort of isotopes? In most problems, you'll be given some type of information to do that. One way that you could kind of do experimentally to sort of figure out the percentage of each of these isotopes and how they come out is through a process known as mass spec. And when you do something like mass spectrophotometry here, we'll flip, maybe it will flip. So mass spec, basically the masses and the relative abundance of isotopes can be measured by doing this type of experiment. Basically, atoms are ionized. They then are sent sort of down a tube, and some of the molecules are broken up into fragments during this ionization. and they're basically kind of separated, determined by their structure of the molecule. They go through sort of a magnetic field, a little electrical field, and sort of are separated really at the end by sort of masses. So they'll come out on sort of the graph at different sort of locations, depending on their masses. And they'll have sort of different sort of peaks, if you will, in terms of their percentages. So that's a way to kind of figure out, the percentages of each of these sort of isotopes. So for example, here, if we look at a mass spec, it gives the relative mass and the relative abundance of each of these guys. And again, here, this is our 35 and 37 for our 2 chlorine isotopes in this case. And again, it also will give you, based on really the size of the peaks there, the relative percentages of each of those isotopes that we use for the relative abundance. Here's sort of a picture of it. Again, your sample comes in, gets sort of heated up pretty good, sends through an electrical field, and also bends through there a magnetic field, and again sort of separates out on the chart as different peaks based on sort of their masses. In this case, the heavier guys here to the right on this, and our lighter guys sort of coming out there on the left as they go through this mass spec. So again, that's a sort of experimental way that you can kind of determine those percentages of the isotopes that are there and their relative masses as they do come out in this sort of process. So why don't we try one here? If copper is 69.17% copper 63, and it has a mass of 62.9396, and the rest is copper 65 with a mass of 64.9278 AMU. What is the atomic mass of copper in AMU? So why don't you do the calculation and see what you come up. Yeah, let's take a look. So we really have 2 isotopes of copper here. We got copper 63. It has a percentage of 69.17% and has an atomic mass of 62.9396 AMU. We also have copper 65, and it has a mass of 64.9278 AMU. In this case, we're not given the percentage there of our first copper isotope, but we do know if these are all the naturally occurring isotopes, our percent of copper 65 should really be 100%, right? Minus our 69.17%. And that gets us 100 minus 69.17. 3003.83. So now we have our missing sort of percentage here of our isotopes, and we do have everything that we need to basically calculate it. So the atomic mass here would be our first isotope. And once again, we're going to convert it into a decimal. So I'm going to, in this case, just move the decimal place 2 places to the left. 0.6917 times the atomic mass of our first isotope. I didn't miss too many numbers there. Try that. There we go. Again, I'm going to add here. I'm going to convert this guy into a decimal. And again, if you wanted to, like I said, you could just divide it by 100 as well. And then times it by our 64.9278 AMU. Now, if we do all that good stuff there, 0.6917 times 62.9396, we add it to basically 0.3083 times 64.9278. Hit equals, we get a 63.55 AMU, which is pretty much what you see there on the periodic table underneath copper. There we go, copper. Any questions on that calculation? Yeah. So again, some variations on this sort of problem is maybe you are given the atomic mass, and you need to find maybe the individual isotope's mass or something like that. So you kind of those type of variations. Any questions on calculating atomic mass or anything like that? All right, so like I said before, not too much in your chemistry career where you're probably whipping out the AMU in terms of calculations and stuff like that. And that's really because a lot of units that are very common to us that we use, especially, for example, in the lab and when we measure things, are masses of grams. So We do need to kind of have a unit that we use that involves grams, and that really is the molar mass, which is sort of what we're going to talk about next. And that's probably, I would say, most of the time, if not all of the time, sort of how you would use those sort of units. That's our calculation. Hopefully they got the same number. Otherwise, that would be embarrassing. All right, so that's good. So before we get right into molar mass, let's first talk about our other favorite thing, which is our good friend Avogadro. And in chemistry, much like in life, we do have sort of words that represent a certain amount of something. So when we talk about, we have a dozen of something, that's 12. If we got a pair of something, that's 2. If we got a gross, it's 144. Pencils, they used to very commonly do that type of thing. So in chemistry, we do have a name that does represent a certain amount of something, and that is the mole. And the abbreviation for the mole there is this guy right here. It is MOL. They had to abbreviate it some way, I guess, so they dropped the E there. Problem with that, though, for a lot of people is when people do see MOL, they automatically all the times think of like molecules when they kind of see that abbreviation. So remember that when you do see the MOL abbreviation, it is a mole and not a molecule, so you don't hopefully mess that up. So pretty much a mole of anything does equal a specific number, which is 6.022 times 10 to the 23. We could do a little bit of rounding there. So really 1 mole of anything will equal 6.022 times 10 to the 23. Now, when we use this is what is known as Avogadro's number. And Avogadro's number, in terms of the units, though, can really be any type of units. So very commonly, this could be atoms. These could be molecules. They could be particles. They could be pizzas, and they could be shoes. Although you do get the occasional shoe question, but most of the time here in chemistry, we do use atoms and molecules. So for the most part, that's usually what you'll use Avogadro's number for. And we can use it really as a conversion factor. Like I said, we could use it as, 6.022 times 10 to the 23 atoms over a mole. Or you can flip it around. A mole is 6.022 times 10 to the 23 atoms, or again, they could be molecules there. It is our conversion factor to go pretty much between those two units. So it is your conversion factor to go really between moles to atoms or molecules, or backwards. And that's a really important thing because, frankly, people learn Avogadro's number and then they just want to use it in every calculation because, it seems very chemistry-like, so why not? And you don't want to do that. In most cases, or in a lot of cases, people, when they do screw up and do that, at least they screw up good in the sense that they will kind of divide by Avogadro's number, then multiply by Avogadro's number, so they cancel each other out. But in case you don't do a bad job of that, you don't want to use it where you shouldn't. So really the rule is you really only want to use Avogadro's number anywhere where a problem either gives you a number or you're asked to find a number that involves molecules, atoms, particles. If there's no mention of any of those things, then you should really leave Avogadro's number on the side there and not use it. So bless you. Sometimes people kind of overuse it. So how can we apply Avogadro's number? Really, you could apply it to anybody from the periodic table. So for example, in 1 mole of hydrogen, there would be 6.022 times 10 to the 23 atoms of hydrogen, which would give you obviously the two conversion factors of 6.022 times 10 to the 23 atoms of hydrogen over a mole, or vice versa, flipping it. You could also apply this to anything that is, say, not an atom or a molecule. So if you had 1 mole of water, that would give you 6.022 times 10 to the 23 molecules of water. So here again, we do see sort of the difference there. Water is a molecule, so we use the units of molecules rather than atoms, like we do with hydrogen. So you can take anything from the periodic table and use Avogadro's number, and obviously you could do it for anything that's a molecule as well. Obviously, when you do punch Avogadro's number into your calculator, you want to make sure you use your exponent button, right? So you want to make sure you use that exponent button so you're not off in terms of your calculation. Any questions on that there? Now, the other unit, which probably I would say out of all these units, is pretty much the one that you use most of the time, and that is molar mass. And molar mass is also taken from the periodic table. It is also that number that's on the bottom. So again, earlier we saw that hydrogen was 1.008. And basically the units of molar mass are grams per mole. And the number always stays with the grams part, and it's always per 1 mole when you calculate the molar mass. So we use really the molar mass as a conversion factor to go between basically those two units. We use it to go between grams to moles, or backwards. That is basically the molar mass from the periodic table is your conversion factor to do that. So something like hydrogen, that means in 1 mole of hydrogen, there is 1.008 grams, or the molar mass of hydrogen is 1.008 grams per mole. Once again, 4 significant figures is where we take it from. We can use the molar mass, like I said, really as a conversion factor. So we could say 1.008 grams of hydrogen per mole, or if you needed to do some dimensional analysis, you could flip it around and use it as a conversion factor the other way as well. You also can, as we talked about when we do some of these labs, you can basically calculate the molar mass from the periodic table from anything that's a molecule as well, or any type of thing from the formula. So if we had something like H2O, we basically would just add up all the parts from the periodic table. So there are 2 hydrogens at 1.008 grams per mole each. That's basically our hydrogens. And there are 1 oxygen at 16 grams per mole. And that's our oxygen. That gives us a molar mass for water, 18.02 grams per mole. Again, the number stays with the grams part. It is per mole. And just like in the other one there, you can use it as a conversion factor. So you can say 18.02 grams of water in a mole. Or if you needed sort of the conversion factor the opposite way around, if you're doing a little dimensional analysis, mole up on top, 18.02 grams of water there on the bottom. So you can use it each way. So molar mass probably going to be used the most, I would say, probably out of all these sort of calculations. Now, it is numerically equal to each other. So earlier we saw something like hydrogen is 1.008 AMU per atom, using Avogadro's number as a conversion factor and so forth. It numerically comes to the same number for grams per mole. So grams per mole is sort of equivalent, if you will, to AMU per atom. Again, the reason we use it more as grams per mole is, like I said before, we go measure things out in grams. So it's a more usable sort of unit. And that's why we use it more often than pretty much any other one. So that's a really important sort of conversion factor to go between those two units, and it is used a lot. How do they all sort of tie together with Avogadro's number and molar mass? They do all tie together, and it is Avogadro's number that's sort of the guy that ties them together. If you had 1 mole of hydrogen, that would equal 6.022 times 10 to the 23 atoms of hydrogen. And that would equal 1.008 grams. So they're all basically related to each other in that sense. Same thing with even our water. In 1 mole of water, that would equal 6.022 times 10 to the 23 molecules of water. And that would equal 18.02 grams of water. So again, that is basically how they are all related to each other. Any questions on any of that there? So take a look at a couple things. So for example, if we had the let's see here, let's do we wanted to know how many grams are in 7.5 times 10 to 26 atoms of copper. So why don't you take a moment there, and we'll take a look here. Copper on the periodic table, as we just calculated, 63.55 is what you see. All right, so see what you okay, let's take a look. So first off, do we need to use Avogadro's number here? The answer is yes, and because we do have obviously atoms involved. So really we need to go from atoms here to moles, and we want to end up in grams, so we want to end up there. And again, it's going to be Avogadro's number as our pathway to go from atoms to moles, and again, our molar mass from the periodic table to go from moles to grams. Once again, we do need the molar mass at some point, so we can take that, and that's basically 63.55 grams per mole as our molar mass of copper. Remember, if we're going to do some dimensional analysis, which we are here, we could use it the other way if necessary. And again, you may not need to. So in this case, we will start with the atoms. So we got 7.5 times 10 to the 26 atoms of copper. Atoms are up on top, so we want to use Avogadro's number here to cancel it. So Avogadro's number does need to go here on the bottom to divide by it. That way the atoms will cancel. That will give me moles of copper. So if I stop the calculation right at this point, I would be in moles of copper up on top. You could get an answer at this point. Again, I probably wouldn't round too much here since you're going to do one more calculation with it. If you don't want to get an answer, you could just continue on with the calculation, obviously, and do it. And again, the importance is shown in dimensional analysis, which you should be doing, is you could clearly see now that the moles are still up on top, which means we do need to get rid of them. So remember, opposites get rid of it here in dimensional analysis. So we're going to use conversion factor there on the left, which basically means we're going to multiply by the molar mass. That's going to be 63.55 grams per mole of copper. The moles of copper will cancel. Once again, a reminder that everything we do up on top are multiplying, and then we're coming back and dividing by whatever there is on the bottom. And if we do that, 7.5 exponent button 26 times 63.55 hit equals, divided by Avogadro's number 6.022 exponent button 23 hit equals. In this case, since the last guy is a 1, gets us something like 79147 grams of copper. In this case, really an exact number. So 2 sig figs would be probably what we should be shooting for here. So if you wanted to, 79,000, or you can do scientific notation as well. Yeah. Any questions on that calculation there? Okay. So let's do a few more here just to make sure everybody's good. All right, so this is the 1 mole of all those guys. This is our conversion factor between our 2 guys there and our pathway. All right. Let's try this. Calculate the number of grams of iron in 15.7 moles of iron. Iron is 5585 there on the periodic table, I believe. All right, let's take a look. So we want the number of grams of iron here in 15.7 moles. So we do not need to use Avogadro's number here. Again, there's no mention of atoms or molecules or anything like this. This is really just a conversion from moles to grams, and that's our molar mass from the periodic table that's going to allow us to do that. So pulling it off the periodic table here, that tells us we have 5585 grams per mole. Or we have a mole is 55.85 grams. So starting with the 15.7 moles, again, we want to go opposite to cancel. So we are going to use it in this form. That's going to give us 55.85 grams per mole of iron. Our moles will cancel. We're going to basically just multiply those two numbers there, 15.7 times 55.85. Going to get us about 876.845 grams. Once again, sig fig wise, probably should reflect off of that number, which is 3 significant figures, which maybe is an 877 on the round there. Grams would be appropriate here. Any questions on that one there? Okay, let's continue through a few more of these here. How many moles of lithium are there in 77.8 grams of lithium? Lithium 6.941, I think. So on this one here, once again, we want moles. We have grams, so do not need Avogadro's number. Once again, it is our molar mass that we're going to use to go from moles to grams. And from the periodic table, gives us two options as conversion factor, 6.941 grams per mole is the molar mass of lithium. Or once again, we could use it conversion factor wise in the opposite direction. So in this particular case, we got 77.8 grams of lithium. Here, grams are up on top, which means we actually do need to kind of flip it around there to use it in our dimensional analysis calculation. Moles will go up on top, which is what we're looking for. The grams there will go on the bottom. Grams will cancel each other out. So we're basically dividing here. So we're taking 77.8 divided by 6.941. Going to give us a 11.2 moles of lithium. 11.2 and a bunch of numbers. But once again, looking here at this number, 3 significant figures there should end up 3 sig figs on the end of the calculation. Any questions on that one there? Yeah, let's roll through a couple more here. How many? Okay, let's take a look. So in this case, we're looking for atoms. We have grams, so we do need to use Avogadro's number, as obviously we're going to end up in atoms. Our pathway here is probably grams to moles and moles to atoms. Again, here our grams to moles conversion is the molar mass from the periodic table. Our Avogadro's number is our conversion there to take it the rest of the way. So that is where we will start, is our molar mass, which once again is 39.10 grams per mole. Or again, if we needed to, we could flip it around to use. So starting with our grams here, 0.551 grams of potassium. Grams are up on top, so we do want to get rid of it. So we will be flipping it around and using it that way. We're going to put our grams there on the bottom. And if we stop the calculation right at this point, we are in units of moles, which is close to what we want. But remember that MOL is moles, not molecules or anything like that. Again, you could get an answer, try to avoid the rounding until the end, or you could continue on with the calculation. I'm going to continue on with the calculation here. We're going to use our Avogadro's number to take us to the end. In this case, we actually want moles to cancel. So we want the moles on the bottom of potassium and actually Avogadro's number up on top so that the atoms remain. So this way the moles will cancel in this case. Once again, we're going to multiply everything that's on the top, making sure to use our exponent button. So 0.551 times 6.022 exponent button 23 hit equals, divided by what's on the bottom, 39.10 hit equals, going to get us an 8.49, looks like maybe, times 10 to the 21. The units here would be atoms of potassium. Yeah. Any question on any of those steps? So again, molar mass from the periodic table, Avogadro's number to take us the rest of the way. Any questions on that? All right, so let's take a look at another one here. We're going to skip these examples. You want to do a couple more. There are those kind of similar to what we just did. Let's take a look at this example here and talk a little bit about it here together. So in this particular case, we're interested in how many atoms of hydrogen, or how many hydrogen atoms there are in 72.5 grams of C3H8O. So in this particular case, we're actually not interested in the entire thing. We're not interested in the entire formula there, C3H8O. We're actually just interested in the hydrogen part of that. So in a case like this, we can actually use the chemical formula as a conversion factor. And the way that we could do that is when we look at these small numbers that are on the bottom, they actually represent the moles of each of those atoms that are present. So from the actual chemical formula there, we could actually come up with three different sort of relationships that we could use. We could say in 1 mole of the entire thing here, C3H8O, there would be 3 moles of just carbon. And again, that would come from the coefficient or the subscript that is there. We could also say in 1 mole of C3H8O, there would be 8 moles of just hydrogen, which also comes from the subscript. And we could say in 1 mole of the entire thing, C3H8O, there would be 1 mole of oxygen. Now, each of those are equality, which means for each of these, you could write 2 conversion factors. So for example, here, you could write for the first one, you could write 1 mole of the entire thing gets us our 3 moles of carbon, or you could flip it around, 3 moles of carbon up on top, 1 mole of the entire thing. So obviously you could do that for, the entire thing. So since we're going to use this as really a conversion factor from going from the entire sort of molecule to each of the individual sort of atoms, or each of the individual elements, and it is a mole to mole relationship here, we do need to get really our whole thing into moles so we can kind of do that conversion. So in order to get us into moles, we do need the molar mass of that compound. And in this case, we do want to just add up all the parts from the periodic table. So to get the molar mass of our C3H8O, there are 3 carbons, each from the periodic table of 12.01 grams per mole. That's basically our carbon. We will add it to 8 times 1.008 grams per mole, which is our hydrogens. And we will add it to, basically, there's only 1 oxygen, so 16 grams per mole from the periodic table, and that is our oxygen. So if we add all that together here, 3 times 12.01 plus 8 times 1.008 plus a 16er, that's going to give us a 6009 here. So we got 6009 grams per mole. That would be our molar mass here for our formula. So really, we're going to use that to convert the entire guy into moles. So that is our first step in this calculation. We're going to take 72.5 grams of C3H8O. We're going to use the molar mass from the periodic table that we just calculated. We want the grams on the bottom so that they cancel. And if we do that right at this point, and if we do get a number, so we'll take a number at this time, 60.09. Going to give us 1.20652. Going to take it out to a few digits, moles of C3H8O. So we've now converted into moles of the entire thing, but remember, we just want the hydrogen. So that is where this relationship is going to come from, and that's going to come from the actual formula itself. And we're just going to use it as a conversion factor. So in this case, we want to get rid of everything, the entire thing. So that's going to go on the bottom. 1 mole of C3H8O would give us 8 moles of hydrogen. So that's what's going to allow us to go from the whole thing to just the hydrogen part. And if we give that a ×8 type of situation, we end up with 9.6521888. Again, taking it out to a few digits there. And again, this is now moles of hydrogen. Any questions on that so far? That is close to what we need, right? We don't want moles of hydrogen, but we actually want atoms of hydrogen. So again, that keyword of atoms means that we do need to use Avogadro's number. So here we would need to use Avogadro's number, 6.022 times 10 to the 23. So the last part of this calculation here would be using Avogadro's number. And we want the moles to cancel. So moles would go on the bottom and Avogadro's number would go up on top in this case. The moles will cancel and that will get us that times 6.022 to the 23. Looks like in this case here, 5.81 times 10 to the 24 atoms of just hydrogen. Clearly, we could do similar calculations for all the other elements that are there, but obviously in this case, we're just interested in hydrogen. You could also obviously do this calculation all together without getting the answer in between. If you do get the answers in between, like I did, I just use the whole number of the calculator, try not to round too much along the way. Any questions on that? So again, you may be asked about some individual element in a formula. And again, that formula can be used as sort of a mole to mole sort of conversion factor for each of those elements. All right, let's try a few more here to finish it out on this stuff. How many moles are there in 23.2 grams of ethanol? And how many molecules are there? Again, carbon is 12.01 there in the periodic table, hydrogen 1.008, and our good friend oxygen still 16, I think. And while you're at it, how many grams of carbon are there in 23.2 grams of ethanol? All right, so give that one a go as well. Let's see how we're doing. So all these questions are sort of related to each other. We want to know in the first one how many moles there are in 23.2 grams of ethanol, which means we do not need Avogadro's number for that part. We do need the molar mass as we're going in this case, grams to moles. So let's take a look first at just that part of it. So obviously we would need to go to the periodic table, look up all that stuff. We got 2 carbons at 12.01. We do have 6 hydrogens, each at 1.008 grams per mole. And the molar mass there of oxygen being 16 grams per mole. And we just have one of those. That gives us a molar mass for this particular compound. Oh, not that. 4607 in this case. So we are going to again use as a conversion factor like we have previously done. So we're going to take our 23.2 grams of ethanol. We're going to use that and going to put the grams on the bottom so that they cancel. Moles of it up on top. Grams will cancel, going to give us for our first guy here 23.2 divided by 23.2. I feel like I wrote the same number in both spots, which clearly doesn't seem right. So let's use the actual molar mass we calculated, 4607 grams there on the bottom. Seems much better. So try that again. Otherwise, I get 1, I suppose. There you go, 4607. All right, so we got a 0.504 moles of C2H6O. Again, doing the rounding based off of obviously that number there, which is 3 significant figures. Any questions on that? Again, use the correct number would be good. Yeah. All right. So it is really the second part here, a continuation of it, which is grams to molecules, and our normal pathway in this case would obviously be grams to moles, which we just did above. And then obviously here we would go to molecules using Avogadro's number. So we're just going to obviously pick it up here from the Avogadro's number part of the calculation. And I'll use the rounded number. And if you didn't, you may end up with slightly different number, but it should be pretty close. In this case here, we want the moles to cancel. So moles are going to go on the bottom. And our Avogadro's number will go on top, which means we are multiplying by Avogadro's number. And this would actually be molecules. Let me get all those units right here on this problem. There we go. And we got 0.504 times 6.022 to the 23. Going to get us 304 on my rounded number times 10 to the 23 molecules here of ethanol. Questions on those first two parts of it. On the last one I made up here, we're looking for how many grams of just carbon in this case. So once again here, this would be a situation where we would want to use the formula as a conversion factor. And if we do that, in this case, we're interested in carbon. So we can see from the formula, and 1 mole of the entire thing, that will get us 2 moles of carbon. So we're going to basically just use that part of it. And we also can just steal this part of it here since we already did it previously. Obviously, if you didn't, you would need to do that calculation. But 0.504 moles of the entire thing, using the formula to take us to carbon. Again, 1 mole of the entire thing gets us 2 moles of just carbon. If I stopped at this point, I would be in units of moles of carbon, which is close to what I want, but I do want grams. So I do need to use the molar mass here. I should use the molar mass of just carbon, right? At this point, not the entire compound, because obviously we're just talking about carbon at this point. So we would use the molar mass of carbon, which is 1201 grams per mole. The moles will cancel in this point, and we will end up with 0.504 times 2 times 12.01, going to give us about 12.1 grams of carbon in this case. Yeah. Any question on that calculation there? All right. Let's take a look at one last one of these types here. What is the mass in grams of 1 molecule of our friend caffeine? Again, carbon 12.01, hydrogen 1.00. All right, so since we're getting in, let's take a look here. We want grams, we have molecules, so that's a key. We need Avogadro's number here. So again, we're going to go from molecules to moles to grams. And again, Avogadro's number first, followed by the molar mass to get us there. So we do need a molar mass at some point. So might as well calculate it up front. That is 8 carbons, it looks like. So we got 8 times 12.01, which is the molar mass there of carbon. Plus 10 times 1.008, which is our molar mass of our hydrogens, plus 4 times 14.01, which is our nitrogens, and I got a couple of oxygens in this case, so 2 times 16 for our oxygens. That is going to give us here a molar mass of 8 times 12.01 plus 10 times 1.008 plus 4 times 14.01 and a 32. 194.2 looks like grams per mole. All right, so we pretty much got everything that we need. We're actually starting with 1 molecule here of our caffeine. C8H10N4O2. So first we're going to do our Avogadro's number here. We do want to get rid of molecules, which means Avogadro's number does need to go on the bottom, and that would be molecules per mole of our caffeine. The molecules will cancel at this point. We have moles. We want to get to grams. So we're going to use our molar mass here to do that. We have moles up on top. So in this case, moles would go on the bottom. Our 194.2 grams would go up on top. That way our moles will cancel. Going to leave us grams. So that's basically 194.2 divided by Avogadro's number. And that should get us something like 3.225 times 10 to the minus 22 grams of our caffeine in this case. Now, you may be wondering, maybe why I went to 4 significant figures. Pretty much one molecule, if you had one of something, it would be more something you would count like an exact number. So you really could lay up as much significant figures as you like. In this case, since the molar mass there was 4 significant figures in this case. Any questions on grams, moles, Avogadro's number, calculating these things? Clearly molar mass, grams to moles, moles to grams, something you do a lot in chemistry. So definitely need to know how to do all these, but for sure that